All right, next one we're going to take a look at is the addition of hydrogen, once again to an alkene. This process is known as hydrogenation. So perhaps you've heard about um, partially hydrogenated fats. Uh, and so this process involves increasing the saturation of a hydrocarbon by adding hydrogen. So it's important to know that this reaction occurs at 150 degrees Celsius. You do have to know that value. And in the presence of a nickel catalyst, a heterogeneous catalyst. So for this one, you don't need to know the mechanism, so just the equation for the reaction will be sufficient. So again, we can write it as either structural formulas or chemical formulas. So I'm going to write it as a, just to change things up, I'm going to write it as a structural formula this time. So we have ethene, and it doesn't have to be ethene, but some alkene, reacting with hydrogen. We have a nickel catalyst, 150 degrees Celsius, so make sure to include both of those. So any reaction conditions, whether it's a high temperature or a particular catalyst, make sure to indicate that either above or below, in this case above and below the arrow. And so what we end up with is, of course, converting our alkene into an alkane. So we go from ethene, in this case, to ethane. Another example of an addition reaction involves the addition of water. This reaction is usually catalyzed by sulfuric acid. Also can be catalyzed by aluminum oxide. So again, just to change things up, I'll write it as structural formulas. Now think of the water here as HOH, maybe? And keep in mind that it's not both sulfuric acid and aluminum hydroxide, it's or. So it'd be one or the other written above the arrow. And so what we do in this case is we're taking an alkene and converting it into an alcohol. So probably should have written the H2O in a different color, just for emphasis. So hydrogen goes to one carbon, the hydroxyl goes to the other carbon, and so we're converting an alkene into an alcohol. All right, lastly, we have a reaction between a nitrile, I'll show you what that is in just a second, and hydrogen. This also occurs in the presence of a nickel catalyst. And so I mentioned before that we can use R to represent carbon chains, so one or more carbons. So a nitrile has this functional group, C triple bond N. And so this reaction occurs with 2 moles of hydrogen per 1 mole of our compound, our nitrile. And again, we have a nickel catalyst. So this is a way of producing an amine. So I'm going to put some hydrogens here just again for emphasis. So we're taking a nitrile, which has a C triple bond N, and converting that into an amine. All right, something you need to be careful of involves the addition reaction with asymmetrical alkenes, and especially the addition of either water or the addition of a hydrogen halide. For example, let's say you have a reaction between propene and hydrogen chloride. Now, there's 2 products that are possible for this reaction. So again, be careful if you have an asymmetrical alkene undergoing an addition reaction, especially addition of either water or addition of a hydrogen halide. 2 possible products, I'm going to show those on the next slide here. So letter I in your notes. So let's take a look at propene. And suppose that the propene is reacting with hydrogen bromide. Whoops, let's fix that, sorry. And in fact, I'm going to scoot this over just a little bit just so my arrows look nicer. Nice, nice arrows. All right, so same as before. So we have the electrons of the pi bond attacking the hydrogen end of this molecule. So we have a covalent bond formed between one of the carbons that is double bonded and hydrogen. And so one of the possibilities is this, where we form a primary carbocation. So this here, and the symbol for that is, that's primary. We have a primary carbocation. And so in this case, the product of this reaction would be 1-bromopropane. Okay, so that's one possibility. Well, why does the carbocation form there? Well, it doesn't always form there. So let's take a look at the other possible mechanism for this reaction. So this time, instead of the hydrogen being added here, let's do this again for emphasis. So we have, there we go. And I'm not going to write the bromine in green. That's fine to leave, I guess, in blue. Instead of the hydrogen being added to carbon number 2, so remember this is carbon number 1, carbon number 2, carbon number 3. Instead of the hydrogen being added to carbon number 2, why can't the covalent bond form between carbon number 1 and hydrogen? Well, that is a possibility as well. So let's again change colors. So we have that's there. And this time, because the hydrogen is being added to carbon number 1, we produce a secondary carbocation. So remember those definitions, primary. We primarily were discussing primary alcohols, primary halogenoalkanes, or secondary alcohols, secondary halogenoalkanes. That terminology applies to carbocations as well. So in the first example, the carbocation has 2 hydrogens bonded to it, or it's just bonded to 1 carbon atom, and so that makes it a primary carbocation. In this case, the carbocation has 1 hydrogen bonded to it, or we can think of it as being bonded to 2 carbons, thus making this a secondary carbocation. And so again, we have the bromine here. That's going to add to that carbon, and so what do we end up with? Again, just for emphasis, I'm going to still write the hydrogen in green so you can see the difference. And so what do we make? We make this time 2-bromopropane. So the question is, in the reaction between propene and hydrogen bromide, what do you make? 1-bromopropane or 2-bromopropane? The answer is sort of yes, you make both. However, they're not going to be both produced in equal quantities. We're going to end up with a situation where we get what's called a major product and a minor product. Major product being the substance that is produced in a greater quantity. And so you'll end up with more 2-bromopropane than 1-bromopropane. Well, how do we know this? And how are we supposed to predict this? So we're going to use something called Markovnikov's rule. So Markovnikov's rule allows us to predict which of these products actually forms. And here's what it states. When hydrogen halides add to alkenes, the hydrogen atom always adds to the carbon atom that is already bonded to the most hydrogen atoms. Therefore, in the reaction above, 2-bromopropane is our major product and most likely to be produced. So why does the hydrogen of the hydrogen halide add to the carbon with already more hydrogens? And the halide, the halogen, adds to the carbon with less hydrogens. Has to do with the carbocation that is produced. And again, I said in the first mechanism, we saw the formation of a primary carbocation. And in the second mechanism, we saw the formation of a secondary carbocation. So it says here, the reason that this rule works is due to something called positive inductive effect. So you can read about that on page 506 of your textbook. It states that carbocations with more alkyl groups, so more carbons basically, surrounding it are more stable due to the ability of these alkyl groups to push electrons towards the positive carbon atom. Consequently, the secondary carbocation is more stable and will be formed in preference to the primary carbocation, which is less stable. So again, due to positive inductive effects, so those alkyl groups pushing electrons towards that carbocation, making it more stable and more likely to be produced than the primary carbocation. Therefore, we end up with 2 bromopropane as the product versus 1 bromopropane. So one more time, if you have an asymmetrical alkene, addition reaction involving an asymmetrical alkene, the halide, or if it's water that's being added, the hydroxyl group will go to the carbon that has more carbons bonded to it, or the hydrogen's going to go to the carbon with more hydrogens bonded to it. If there's ever a debate between which carbocation will form, if you have primary versus secondary, secondary carbocations are more stable than primary, and therefore that's where the carbocation will form, and that will lead to the formation of a particular product. All right, so that concludes our lesson on addition reactions. Next time we will talk about, I believe, substitution reactions of halogenoalkanes. Thanks for watching.